Section 7A covers some basic ideas of probability. We'll do some simple problems and understand basic terminology that is used in probability. We'll do problems 1 through 6 in this video. In everyday life, we're always trying to predict what's going to happen in the future. For example, I can say today, it's going to rain tomorrow. So that's a prediction I'm making. What I'm watching is the weather, and I'm making a prediction about whether it will rain or not. So if the experiment or the random phenomena that I'm watching is the weather, it's called a random phenomena because um, the result of this particular experiment of watching the weather is not predictable. So if I'm watching the weather, I might want to know if it's going to rain, that's one outcome, or not rain. So these are the two basic possibilities which are called outcomes of this particular experiment of watching the weather. So let me call it S. So if the only two outcomes I'm interested in are whether it'll rain or not rain, then those are the only two outcomes of this experiment. Now, each outcome can be considered as an event. So, what's an event? Event is uh, either one outcome or a set of outcomes, one or more outcomes. Let's look at a basic experiment just to understand the definitions better. So, we look at the first experiment and the examples. A basic experiment of tossing a coin. It's a random phenomena or a probabilistic experiment because the outcome of this experiment is not definite. Any one of the two things can happen. You could either get heads or tails. So the two basic outcomes of this experiment are heads or tails. We write it as a collection. It's the set of all possible outcomes. If you remember uh, the set notation, we use braces when we write down a collection of objects. So the set of all outcomes is denoted by, let's just call it S, and it's H or T. So how do we describe H? It's the event of getting heads. So that's an outcome. That could also be called an event. T is getting tails, and that is an outcome. And the event can also be written as a set containing T. Now, the second experiment, another basic experiment that we always discuss in probability, is rolling a die. So this is our second experiment. Rolling a die, it's a random phenomena because the possibilities cannot be predicted. So when you roll a die, any one of the 6 outcomes could happen. So the list of all outcomes is 1, 2, 3, 4, 5, and 6. So we write it as a collection. Let's call it S. So that's the set S of all possible outcomes. Let's look at certain events in this experiment. So we have the event E, and the description of the event is getting an even number. So in this particular experiment, what are the possible even numbers that we could get? Out of all the numbers 1 through 6, 2, 4, and 6 are the only even numbers. So the collection of objects 2, 4, and 6 is called the event E. So the event E can be described using words. It can be denoted using a letter in uppercase, or it can be written as a set. Let's look at the second outcome, or not really an outcome, it's an event, getting an odd number. So what are the odd numbers possible in this particular experiment? The odd numbers are 1, 3, and 5. These are the only odd numbers. So an event can be described in words, getting an odd number. It can be denoted by letters in the uppercase. In this case, we've used O, or it can be written as a collection of objects in braces. Now, another example of an event is getting a 9. And you're probably wondering, is it even possible to get a 9? And you're right, it is impossible to get a 9. So out of the possibilities 1 through 6, none of them fit the description 9. So therefore, in this experiment, 9 is impossible. So how do we write this as a collection of objects? It is a collection, however, a collection of nothing. So that's called an empty set, if you remember from before. We know the definitions of the terms outcomes and events. Outcome is a basic possible result of an experiment, and an event could be one or more outcomes. Now, probability of an event is a quantity, it's a number. So the probability of an event is really a number. So for example, if I say, what is the probability, P, of getting heads in the experiment of tossing a coin, we'd say it is a quantity half. So it's a number, or we can also write it as a percent, because a percent is really a fraction, and 50% is half. So the probability is just a quantity. If I say what's the probability of an event, the answer is a number. And in addition, it's a number between 0 and 1. It cannot be greater than 1, it cannot be less than 0, but it can be 0 and it can be 1. So what happens when the probability of an event is 0? What that means is that event is impossible. It is never going to happen. So the next example is if the probability of an event is 1, then it's certain that the event is going to happen. So it's a number between 0 and 1, and it includes 0 and 1. So that's probability. Theoretical probability. What is theoretical probability? When you figure out probabilities using logic. So if the experiment is that of tossing a coin, and if I say, what's the probability of getting heads? We don't need to do an experiment to say that it's equal to half, and that is the same as the probability of getting tails. So we use our logic to figure out probabilities. So if you're finding out probabilities without actual experimentation, then it is called theoretical probability. Now let's look at the definition of equally likely outcomes of an experiment. So when are outcomes equally likely in an experiment? So we look at the familiar example of tossing a coin again. When we toss a coin, the probability of getting heads is the same as probability of getting tails equals half. Both the outcomes, getting heads and getting tails, are equally likely to happen, and both are equal to half. So those are equally likely outcomes. In the second experiment, look at it once again. We're talking about rolling a die. The outcomes are 1, 2, 3, 4, 5, and 6. Now, the probability of each outcome is, let's say, for example, 1 is equal to 1 out of 6, because any one of these could happen, and the chance of each one happening is exactly the same. So the probability of getting a 1 is equal to 1/6, which is the same as probability of getting a 2, which is the same as probability of getting a 3, etc. So they're all equally likely, and these are called equally likely outcomes. So experiments 1 and 2 are experiments with equally likely outcomes. Examples of outcomes that are not equally likely, let's look at example 3. We toss 2 coins, and now we're going to observe the number of heads. That is what we're interested in. So what are the outcomes of this experiment? The outcomes of this experiment are 0, 1, 2, because um, the number of heads is 0 when we have two tails after tossing two coins. The number of heads in either one of these cases is 1. When we toss two coins, we could get heads first, then tails, or tails first and then heads. Either one of these would have one head. So there are two possible outcomes for which um, the count is one head. What if we get HH? Heads on the first toss, heads on the second toss, then that would give us two heads in this experiment. So let's look at the outcomes. So we're looking at the outcomes 0, 1, and 2 because we're counting the number of heads. Probability of getting a 0 is 1/4. It's 1 out of the 4 because out of the 4 possible outcomes, TT is just 1 out of those 4. And similarly, probability of getting um, 2 heads is again 1/4 because it's 1 out of the 4 possible outcomes. However, probability of getting 1 head is 2 out of the 4 possible outcomes. So that would be 2/4, which is really equal to 1/2. So now we have listed the probabilities of each one of these outcomes, and clearly they're not equally likely because the probability of getting 0 is not the same as probability of getting a 1. So clearly this is an example of an experiment where the outcomes we are interested in are not equally likely. We look at example 4. We consider a spinner that we use in usually board games. So the outcomes in this particular spinner that I have here are green, red, or blue. You could get any one of the 3 colors when you spin the needle in the middle. So what is the probability of getting blue? Blue is 1/4 of the entire circle, so that's probability 1/4. And similarly, we can kind of figure out that probability of getting red is half of the 1/4, so that's 1/8, and the rest of it is getting a green. So again, this is an example of if outcomes that are not equally likely. Empirical probability is different from theoretical probability. In empirical probability, we calculate probabilities based on observations from an experiment or the data collected from surveys or questionnaires. So let's look at an example. Suppose we base our results or probabilities on the data that are collected in hospitals. And usually when you walk into a doctor's office or you walk into a hospital, you give a lot of information about your health and physical conditions and other things in the form of questionnaires. So let's assume that data are collected in a hospital. And based on that collected data, if the hospital gives this result, probability that some random person in the United States is blood type A positive is 34% or 0.34, then that's called empirical probability. Now, once we start calculations of probabilities, we're going to use lots of formulas and counting techniques. The most basic counting techniques, the most basic of counting techniques is called the multiplication rule. So we have the multiplication rule. Let's look at this. This is an important rule because a lot of counting techniques are based on this particular rule. If a certain task can be accomplished in m ways and another task can be accomplished in n ways, then the two tasks together can be accomplished in m times n ways. This is a basic rule. Let's look at an example of where this can be used. Now, suppose I have two types of skirts and three types of tops in my closet. How many different combinations of these two can I wear? So we're going to wear a skirt and a top. And our outfit is complete only if we do both. So we need to do both. Wear a skirt and wear a top. How many different choices of skirts do I have? I have two choices of skirts and three choices of tops. So I can go skirt one, top one, or I can go skirt one, top two, or skirt one, top three. So basically, I can wear my first skirt with three different tops. Or I could switch to skirt two. I could wear it with top one. I could wear skirt two with top two. I could wear the same skirt top two with top three. So there are six different ways of in in which I can wear two skirts and three tops. So clearly you can see that I didn't have to list all the outcomes. I could have just multiplied 2 with 3 to get the total number of outfits possible with two skirts and three tops. That is called the multiplication rule. Although it seems very basic, uh, many counting techniques are based on the multiplication principle.